So now that we've talked about how to name things and how, the difference between protons, electrons, and neutrons, now we can start to have a conversation about chemical reactions and the next steps here. So what I like to do is start to look at different molecules and what these things, where they came from and how they work. So if let's start with a simple example of water. If we have a molecule of water, and we look at a molecule, it consists of one atom of oxygen and two atoms of hydrogen. And each of the atoms of hydrogen has one mass unit each, and there are two of them. So they have a total of 2 mass units. So in water, there are 2 units of hydrogen, and then for mass, and then for the oxygen, there is actually 16 mass units. Now, when we're talking about mass units, remember the thing that's in the atom that actually weigh some amount, the significant amount, are the protons and the neutrons. So when we're talking about mass units, we're really talking about protons and neutrons that are making this up. What we know from this compound, if we take the number of mass units, oxygen is 8 times the mass of hydrogen. And that's always going to be the case, regardless of the amount of water. If we have a billion water molecules or a lake or an ocean of water, that's going to be the ratio. It's an 8-to-1 ratio. And it doesn't matter where it came from. It doesn't matter if it rained on you or if you pull it out of a pond. That water is going to have the same ratio of oxygen to hydrogen in terms of its mass. So you can see that here if we have a bunch of water molecules. This ratio is the same in example A versus example B. Some of the successes of Dalton's atomic theory that we've been talking about is one of them is the law of conservation of mass. So it doesn't matter if we rearrange them or react them, the atoms don't change in the mass. The law of definite proportions. So if we're talking about water or we're talking about sulfur dioxide or sulfur trioxide, I'm going to show you an example in a second. Those different ratios are maintained as well for atoms and the individual contribution of those atoms to make up the whole molecule. So the law of multiple proportions was not yet discovered. That one, it wasn't necessarily incorrect, but it kind of explains some more of this. So for example, if we have sulfur dioxide, we have one sulfur atom and 2 oxygen atoms. Then we are able to compare that with sulfur trioxide. These are going to have different properties, these 2 different molecules, and the ratio is going to be different. So if we're looking at the mass of sulfur, the sulfur dioxide versus sulfur trioxide, if we have 32 grams of the sulfur, we're going to have different amounts of oxygen. But these are also 2 different types of compounds that are making those groups up. All right, so one of the things we're going to talk about are now chemical reactions, the rearrangement of these things. So when we have one or more substance to make a new substance, that's a chemical reaction. And the way that we depict this is typically not with pictures, because that becomes difficult to, do your homework on or explain to someone else without, software to create these images with. Instead, we're going to write them out in this format down below. So this would read 2 hydrogen molecules in the gas phase react with 1 molecule of oxygen in the gas phase to produce 2 H2O or water molecules in the gas phase. So this is saying it's balanced, and we'll talk about that, which basically means we have the conservation of mass. We keep the things are still there on the left and the right side, they're just rearranged. So this would be a balanced equation. Reactants are always on the left, products are always on the right. And the arrow is going to point from the reactants to the products. So words to write that all out would be kind of difficult and not easy to follow. But this is on the bottom. This is how we are going to be writing our chemical reactions to mean the same thing. Here's another example of methane gas forming. Again, reactants and products. The arrows means to reacts to yield. So this would be methane plus 2 molecules of oxygen react to yield 1 molecule of carbon dioxide plus 2 molecules of water. So here's just, again, some more how you would read these, how you would say this. I said before 1 part methane, 2 parts oxygen. That is kind of the same idea. This can represent a single molecule or 2 molecules to form these, or it could be parts. You can think of cooking. It could be like 1 cup and 2 cups. It's just you need this ratio is important. You 1 of these and 2 of these, but you could have 1 million of these and 2 million of these would react to produce 1 of these, 1 million of these and 2 million of these. So that the ratios, these numbers in the front before the molecular equation, those are going to be really important, and we're going to use those to understand and using factor label method system to solve problems when we start to ask, okay, so let's say I have so much of this, how much am I going to produce? So these are going to be important moving forward because they are helpful in, and we know the conservation of mass, they allow us to predict how much we're going to create of our product. And remember, the only way that this works out and allows us to predict the products of a reaction is because we have this conservation of mass idea. And so the number of atoms we start with, we have to have the same number of atoms we end with. They're just maybe rearranged in a certain way. So methane, the last example, this is just a picture showing you the same concepts. 1 part methane, 2 parts oxygen, rearranged to form 1 part carbon dioxide, 2 parts water. And all of these, if we add these, we have 4 hydrogens on the left, 4 oxygens, 1 carbon, the same number of each of those elements on the right side. We are going to start to do some accounting to make sure that we have the same number of products on the products and reactants, so that we know that we have the conservation of mass. If that's not true, then we're not going to be able to do some of the calculations that we want to do in order to determine maybe how much product we might receive after we do a chemical reaction. For this accounting, then we need to take all of these elements that have a carbon. I have a hydrogen. I have an oxygen on both sides. And this number in front is the number of molecules. So the number in front describes the number of molecules in that reaction. This 13 is, there are 13 molecular oxygen molecules. Remember, the subscripts refer to only the element that's right in front of it. So there are 4 carbons in this element. There are 10 hydrogens in this molecule. So when I do this, I need to multiply that value throughout the molecule. So for carbon, I have 2 times 4 is 8. 2 hydrogens times 10 of those in the molecule, that's going to be 20. And then finally, 13 times 2 is 26. The same thing happens over here. We have 8 carbon dioxide molecules. I'm going to multiply that through. Carbon, 8 times 1 carbon, 8. Then we have, I'll move down to the oxygen, 8 times 2 is 16. Then we come back up here, 10 times 2 for our hydrogen. And then I have another oxygen molecule, 10 times 1 equals 10. If I add up all of those, 26. And now what you should do is you should notice now we need to look at the accounting. I have 8 carbon, 20 hydrogen, 20 hydrogen, 26 oxygen, 26 total oxygen. Great. So both sides balance. This is a viable chemical equation. So now it's your turn. I want you to account for both of these. Remember, we have the reactants on the left and the products on the right. I want you to account for the nitrogens, the hydrogens, and oxygens on the left and the right. And so how many of each are on both sides? And is it balanced or is it not balanced? So upload your answers to our Blackboard space. I want to just make a note about these polyatomics and when we're balancing equations. This is a useful chart to have handy when we're doing some of these things because a lot of times these elements will kind of move around together. So you can kind of avoid having to kind of recount all of these groupings as long as you're keeping track of the different kind of parts here. So if I have a ClO2 or a ClO3, that these elements might shift around from one element to and kind of pair with another. So let's say we have like lithium or potassium, right? They might change partners, but this grouping might just kind of move around. So you can just kind of keep those as a grouping. You don't necessarily have to break them down into their fundamental elements like chlorine and oxygen. You can certainly, it should work out either way, but sometimes it goes a little faster if you kind of group these. And sometimes I will try to do this, but sometimes you will notice that these elements are a lot of times not written with brackets or parentheses around them. So you'll have to kind of be able to see sometimes if it's a polyatomic ion, that it is a polyatomic ion that can fall apart. So it's just something that to be aware of to make sure. And then I will try to put these in parentheses, but just recognize that other textbooks or other sources won't always put those in parentheses for you. So we're going to start off with looking at some ionic chemical reactions. And a lot of times this is really, how do we make an ion? An ion is a charged element. And the way that we will make an ion is by the elimination of an electron. So sodium, we spoke about during the periodic table trends idea. Sodium will typically be able to lose an electron fairly easily. Chlorine, luckily, likes to accept electrons. So when that happens, we get a positively charged sodium because the electron left it, the negatively charged electron left, and then it bumped onto the chlorine or the chloride now. So this is the ionic form of both of these. And then when they come together, they will create a salt compound. Typically when we're looking at ionic compounds, these are really lattices. So if you take salt from, a salt shaker and look at a little grain of salt, there are thousands and millions of elements of chloride and sodium ions in there. They're packed together in a crystal structure, and they are, there's not really one sodium doesn't belong to any one of these 4 chloride ions that are associated with it. They kind of all are sharing that positive negative charge, and they're distributed evenly. When we do this for accounting purposes, we just use, for the formula unit, we use the smallest whole number ratio. So for sodium chloride, it's a 1-to-1 ratio for every, right? And that means that we're canceling out the positive and negative charge to make it be 0. So the least number of elements that we can combine to make a neutral compound, that's what I'm talking about with the whole number ratio to neutralize it. So because this is just a +1 and a -1, just 1-to-1 ratio cancels out that charge to give us a 0 ratio. Now, when we get to other elements that have +2, +3, +4, +3, 7, whatever charges, then we can have different ratios of these that will have to be as the ratio for canceling out the charge. We'll look at that in a second. So one of the things we don't want to do is, for example, if you have sodium chloride, it's 2 sodium and 2 chloride atoms. That's not how you would write it, because we can simplify that. We can just have 1 sodium element, 1 chloride element, and that's enough to cancel out that charge and give us a 0 charge. So this is the formula unit, should be the most simple form of that ratio. Here's some rules for writing ionic formulas. The cation, the positively charged element, is given first in the formula. The subscripts must produce a neutral unit. So if I have a +2 and I have a +1 element, I need 2 +1 element or -1 elements. I need 2 of those minus elements to cancel out. So the end result, when those things come together, we have to have a neutral compound. Subscripts must be the smallest whole numbers possible. That's where we're simplifying it to the least number of elements given. And the charges on the ions shouldn't be included. So they're not part of that final, the charges aren't part of that final thing. You'll be able to get that information from that small unit formula, but they're not included there. Again, no subscript. It implies that there's just a 1 there. And let's look at some examples here. Magnesium oxide. Magnesium is from group 2A, so if you're looking at your periodic table, it's in the second group, so the second column. And it typically, those are going to form +2 ions. The Mg +2, so that's one of the elements we're going to look at. And then with oxygen, it's going to form, it's in the 6A column, so a couple groups away from the noble gases, it's going to form a -2 ion. So these two coming together, if we have a 1-to-1 ratio, that gives us an electrically neutral particle. And so the formula is going to be magnesium oxide, MgO. So that is how we would put those together. It's the simplest form with the lowest whole number possible for both of those. One thing I want to talk to you about is this idea of the crisscross rule. So it takes into consideration the magnitude of the charge. So that means what the charge value is. Is it a +1, a +2, +3, etc.? So when doing this, again, this helps us. We want to make sure the subscripts are reduced to the lowest number, but the crisscross rule helps us understand how we can get these things to come together. Let's look at an example. So aluminum, a +3 element for aluminum, and then oxygen, -2. How do we put these together so that we can get a neutral element? So we think about the crisscross rule. Crisscross rule is you take the charges and you swap them. You put them from the charge spot in the upper right-hand side to the other element's lower subscript value. So now I'm going to write this out. So we have aluminum oxide. I've taken that +3 charge up here and I've moved it down below to refer to how many oxygen elements we need. And then the oxygen's a -2. I put that down by the aluminum. Okay, so does that make sense? What does this tell us? This says that we have 2 +3 aluminum, right? And that is going to give us, if we add those charges together, that gives us a +6. Oxygen, we have 3 of those, add a -2, and that gives us a -6. So that overall charge is 0. This is just a quick, easy tool that we can use to generate our simple formulas for ionic compounds. All right, one more of these. What we're going to do is we're going to take this element, we're going to move these down, right? So we'd have, oops, sorry, this should be a capital M. And then we have an oxygen. right? If I did the crisscross rule, I would have 2 magnesium and 2 oxygen. Well, remember, we need to make sure that that's the simplest ratio. And so because this is divisible by 2, we can get the MgO. That's the most simplified version. But it gives us a starting point, at least, especially when we're mixing the magnitudes of those charges. That's a crisscross rule is a helpful starting point. Okay, your turn. So I want you to look at which of the following is the correct formula for the formula unit composed of potassium and oxygen ions. Where do you begin with this? So determine what the predicted ionic charge should be for each of the atoms. Again, you want to look at where it is located on the periodic table and use that to look at trends. What are the typical charges for potassium based off of where it is on the periodic table? What about oxygen? If you don't remember, you might have to go to a previous PowerPoint presentation, the last one where we talked about the charges and some of the trends and some of the expected patterns for how charges are set up on the periodic table. Use the crisscross rule to move those charges to the subscripts, and then that should give you the answer. So upload your answer in our discussion board. Another discussion board question, so upload your answer to the discussion board. Give me the which of the following correct formula for the formula unit composed of iron, 3, and sulfide ions. Here's another learning check with polyatomic ions. Same thing happens. We're going to, and feel free to put parentheses around and make sure that charge, that whole entire molecule is charged. So the combination of all of those creates a charged state. And so put these together, same idea with the, I've given you the charges already, and you'll just do the crisscross rule and then make sure that makes sense to you. Upload that answer onto our discussion board. In addition to ammonium and phosphate, I'd like you to look up that groups on that list that I gave you for the table for the polyatomics. I'd also like you to look up strontium and nitrate and tell me what that ionic compound formula would be as well. Strontium nitrate. I also briefly want to just introduce you to this concept of hydrates, sometimes with some salts that you might order from various chemical companies. You'll notice that they'll have this little dot and then water behind it. So these are called hydrates, and basically the crystals that form, they're hygroscopic, so they'll actually grab water from the air and they bring those into themselves. So sometimes you'll get these little packets in certain electronic things or in a bag, for example, and they have these little kind of beads. Those suck in water so that it doesn't ruin your electronics or ruin your beef jerky, for example. They'll have those things in them to suck the water out of the air to reduce the humidity. So they're helpful. There are a lot of these types of salts that will do this. And just so you're aware, typically different salts might take on different amounts of water. So calcium sulfate likes to take on 2 water molecules for every molecule of this. Sometimes they'll take up 4 or 5 or 6, but that will be defined in that salt. So it's not tightly held, but it does suck it up, and it changes. Again, when we start talking about, I want to measure out so much salt, when you're measuring this out, if you know how much water is associated with that, you then can put that in your calculations. So typically these can be removed by heating it. Sometimes people don't really care that much that there's water in it, and they'll just account for that when they're pulling out their calcium sulfate, for example. They'll just make sure they add enough so that they know that they get enough of the salt in the solution they're making. Here's an example of a hydrate calcium sulfate with 5 units of water associated with it. It's blue, and then when you heat it up, that water evaporates out and then it turns white. Just something to recognize that hydrates exist and how to kind of deal with them. And this is just the chemical reaction that's happening here. we have the hydrate with the bullet kind of, and they're written right next to each other, versus plus water, where the water kind of left the salt, but it's still, you still have to account for it to create a balanced equation. So now I want to talk about naming hydrates briefly and quickly. So these Greek prefixes, we've talked about mono, di, tri, tetrapenta. This is just, calcium sulfate with 2 dihydrate, cobalt chloride, hexa, tri. So basically, typically these Greek naming systems are used for how many of those water molecules are associated. And here's the complete list up to 10. So that concludes right now what I wanted to talk to you about naming some simple ionic compounds. And next we're going to start talking about how we can take some of these chemical reactions, and we're going to start utilizing that information in the chemical reactions to start solving some problems. If we want to mix solutions, how much do we add? How much are we going to get out of that chemical reaction? So this is the next step in that process.